Welcome to RNA's Deep Dive.
The Invisible Web, Engineering the Global Handshake.
We have spent a pretty significant amount of time as original researchers mapping out the physical and digital architecture that powers the modern internet.
Right, the real bare metal stuff.
Exactly, from the submarine cable topologies lying at the bottom of the Pacific.
All the way to the complex BGP routing tables that basically hold the whole thing together.
And our mission today is straightforward. We want to shortcut your path to understanding how a single keystroke turns into this massive global exchange of information.
No elementary info overload. We are analyzing exactly how this ecosystem functions from the ground up to the application layer.
Right.
And we really need to talk about why this matters to you. Because whether you are actively debugging a monolithic code base, architecting a scalable cloud network, or, maybe you're just deeply curious about the sheer engineering miracle happening behind your screen.
It is a miracle, honestly.
It really is. Understanding this invisible infrastructure fundamentally changes how you interact with the digital world. It shifts you from being just a consumer of endpoints into someone who can actually manipulate the systems dictating your daily life.
Okay, let's unpack this. We have to start by demystifying two terms that, frankly, even seasoned tech professionals sometimes use interchangeably.
Oh, the web and the internet.
Right. When they are actually entirely distinct layers of the OSI model.
Completely different.
The internet is the underlying network of networks. It's the physical, hardware-level infrastructure. The web, however, is simply an application layer service.
Specifically HTTP and HTTPS.
Exactly, running right on top of that internet. We all know the classic, somewhat tired public library analogy.
Where the internet is the physical library building.
Right, the web server is the shelving. The website is a specific section like history.
And the web page is the HTML book you pull off the shelf.
Yeah.
What's fascinating here is how relying on that ELI5 analogy actually limits your architectural understanding. It completely misses the sheer scale of the system.
Because it's too human-centric.
Exactly. Yes, if a web page is a book, then your web browser, like Chrome or Firefox, is the software you use to retrieve and read it.
Mm-hmm.
And your URL is the Dewey Decimal System.
Right.
But that implies a human scale. It ignores the fact that the vast majority of traffic today isn't humans reading HTML books. It's web services.
APIs, microservices.
Yes, firing JSON payloads back and forth millions of times a second without a human ever looking at a screen.
That's a great point, my co-host. If you conflate the web with the internet, you forget that the internet also powers email protocols, FTP, peer-to-peer networks.
IoT devices communicating on entirely different ports.
Exactly. The web is just the most user-facing service sitting on port 80 and 443.
Which brings us to the actual foundation supporting all those ports. Because people love to throw around the word cloud.
Oh, the ethereal cloud.
Right, talking about their data just floating in the sky. It is a brilliant marketing term, but we need to ground that metaphor right now.
Heavily ground it.
The internet is heavily, undeniably physical. It is mostly fiber optic strands, no thicker than a human hair, and copper wires, physically buried in the dirt and laid across the ocean floor.
Sure, satellites and 5G networks play a role at the edge.
But the heavy lifting, the global backhaul, is done by physical glass and light.
So let's follow a packet of data locally. In your house or your server rack, you have specific hardware managing this traffic. First, you have a network switch.
Operating at layer 2.
Right. It's a traffic cop mapping EMA addresses to physical ports, making sure a local message hits only the intended target device within a specific local network. It doesn't care about the outside world.
But the outside world is where things get incredibly complicated. That's where the router comes in.
Operating at layer 3.
Exactly. It connects entirely different networks. It reads the IP addresses on the data packets and determines the most efficient path forward.
And for you listening at home, you know that plastic box your internet company gave you?
The one flashing in the corner of the living room.
Right. That is a massive oversimplification. It's actually a switch, a router, a wireless access point, and a modem all crammed into one overheating chassis.
It really is doing too much. And that modem is the gateway. It modulates and demodulates the digital network information into a format, like analog frequencies, that can actually travel across the coaxial or optical infrastructure.
And all of this connects back to your ISP, your internet service provider.
But ISPs aren't just selling you access. They are managing massive, specialized enterprise routers running BGP.
Border Gateway Protocol.
BGP is essentially the duct tape of the internet. It's the protocol that ISPs use to announce to each other, hey, I know the fastest route to these specific IP addresses.
And because access to this physical hardware can be heavily restricted, we see distinct network classifications based on who gets to use them.
Right, like your classic internet.
A strictly private network restricted to members of a specific organization. Traditionally, this was a firewalled castle.
But modern organizations are realizing that physical location doesn't equal security.
Hence the move towards zero trust architecture.
Exactly. But I'd push that even further. The real complexity comes with the extranet.
Okay, break that down.
An extranet is a private network, but it punches highly specific authenticated holes through the firewall to allow limited access for external partners or B2B API integrations.
So understanding where your traffic sits physically, whether it's traversing the open internet or an encrypted extranet tunnel, is the absolute bedrock of modern cybersecurity.
It is. Now, with billions of these devices connected by submarine cables and BGP peering agreements, every single device needs a unique mathematical identifier.
Because if you don't have an address, packets can't find you.
Right. This is the IP address. You can think of an IP address like 192.0.2.172 as a geographical routing locator.
You have private IPs assigned dynamically by your router for local use.
And a public IP assigned by your ISP that represents you on the global backbone.
But that specific format, the 4 blocks of numbers, is IPv4. And quite frankly, partner, it's a legacy system.
It is. If we connect this to the bigger picture, the tech industry faced a massive existential infrastructure crisis about a decade ago.
Because IPv4 only allowed for about 4.3 billion unique addresses.
Right. And with the explosion of smartphones, smart TVs, IoT sensors, and everything, we literally ran out of numbers. We mathematically exhausted the supply.
So we had to rely on a massive band-aid called NAT, or Network Address Translation, just to keep things running.
Hiding dozens of private devices behind a single public IP.
Which is an absolute nightmare for peer-to-peer routing.
It forced the global upgrade to IPv6, which uses 128-bit addresses.
And the number of unique combinations there is staggering. You could assign an IP address to every single atom on the surface of the Earth and still have plenty left over.
But dual-stack routing, running IPv4 and IPv6 simultaneously, is still a huge headache for network engineers today.
Oh, absolutely. But as an end user or even a front-end developer, you rarely interact with raw IP addresses anyway. Humans are just terrible at remembering random hexadecimal strings.
Well, rely on domain names, like Mozilla.org, as human-readable aliases.
And to translate that domain name into the actual IP address the router needs, we use DNS.
The domain name system.
DNS. There is a running joke in the developer community. Whenever a complex system completely fails for seemingly no reason,
It's always DNS.
it's always DNS. Your browser essentially queries a hierarchy of DNS servers, starting with your ISP's local resolver all the way up to the global root servers, to find out the exact IP address that corresponds to the domain you typed.
But it's not a simple one-to-one translation, and this is where modern engineering really shines.
Yeah.
Enter load balancing.
Crucial stuff.
If a massive service like Netflix or Google only had one IP address pointing to one physical server, it would meld into the global traffic in seconds.
Literally seconds.
Instead, a single domain name can resolve two entirely different IP addresses depending on geographic routing protocols like Anycast.
Right. So if you query a domain from a laptop in Tokyo, the DNS resolver recognizes your location and hands you an IP address for a data center offline.
And if a massive earthquake knocks that Tokyo data center offline,
The health checks fail, the DNS records update almost instantly, and suddenly that exact same domain name routes the next user to a server in Sydney, Australia.
it optimizes latency and provides incredible fault tolerance.
Which perfectly transitions into how that data actually makes the journey from Sydney back to Tokyo. When you download a massive dataset or stream a video, it is not sent as one continuous stream of zeros and ones.
No, it is aggressively chopped up into tiny discrete units called packets.
Let's dissect a packet, because it's not just raw data, it has 3 distinct sections. First is the header.
Which carried all the vital metadata.
Right, it has the source IP, the destination IP, and crucially a sequence number. Because packets might arrive out of order, the sequence number tells the receiving computer how to stitch them back together.
It also contains the TTL, or time to live, so a lost packet doesn't just bounce around the internet forever.
Exactly. Then you have the payload. That's the actual core data you care about.
The goods.
The goods. And finally, the trailer, which contains a cyclic redundancy check, or checksum.
A mathematical formula the receiver runs to verify the payload wasn't corrupted by electromagnetic interference along the copper wire.
The brilliance here is packet switching.
Contrast this with older telecom infrastructure. which relied on circuit switching. If you made a phone call in the 1980s, a physical, dedicated copper path had to be held open between you and the receiver.
And if a tree fell on the line, the connection died.
Exactly. Packet switching, however, is dynamic.
Every single packet of a single image could theoretically take an entirely different geographical route across the globe to reach its destination, depending on which routers are congested at that exact millisecond.
Sure, but I would actually push back slightly on circuit switching being a complete relic.
Oh, really?
Yeah, in massive modern AI data centers, we were actually seeing a return to optical circuit switching to handle the massive sustained throughput required by GPU clusters.
Wow, that makes sense for that kind of scale.
But on the public internet, packet switching remains king. And it brings up the vital distinction between protocols, specifically TCP versus UDP.
That's a critical distinction. TCP, Transmission Control Protocol, is the meticulous accountant of the internet.
Very meticulous.
It requires a three-way handshake to establish a connection, and it demands an acknowledgement for every single packet. If a packet gets dropped, TCP pauses and forces the sender to retransmit that specific chunk.
It guarantees delivery, which is why we use it for loading web pages or downloading software.
But that guarantee introduces latency.
Exactly. If you are coding a high-frequency trading algorithm or a real-time multiplayer game, you don't want TCP. You use UDP, User Datagram Protocol.
The Honeybadger of protocol.
Yes. UDP just blasts the packets at the IP address and doesn't care if they arrive.
Right.
If a frame of video drops during a live stream, you don't want the stream to pause to fetch it.
Right, you just want the next frame immediately.
Here's where it gets really interesting. Let's put this entire stack together and walk through the exact life cycle of a modern web request.
I love this part. It all operates on a client-server architecture. It starts with the URL, the Uniform Resource Locator. Let's look at a dummy one. developer.mozilla.org/us.
Okay, break that down.
The HTTPS is the protocol. The FES means it is secured by TLS, transport layer security, encrypting the payload so ISPs can't read the content.
Mozilla.org is the domain name.
Developer is the subdomain, routing you to a specific service cluster, and NUS is the path, indicating the specific resource.
So when you hit enter, you initiate a heavily orchestrated lifecycle. Step 1 is the DNS lookup we discussed.
Right.
Once the browser has the IP, step 2 begins. The TCP handshake, followed immediately by the TLS handshake to establish encryption keys.
Step 3, the HTTP request. Your browser sends a specific verb, usually a GT request, asking for the root document.
Step 4, the server response. The server application logic processes that GET request, queries a database if necessary, and sends an HTTP response containing the raw HTML payload.
And finally, step 5, parsing and rendering. Your browser reads the HTML from top to bottom. But wait, it hits a link tag for a CSS file.
It pauses.
Right, it opens a new request for the CSS, it hits a script tag for JavaScript, it fires off another request, it's constantly downloading these concurrent assets, building the document object model, or DOM, and finally painting the visual interface on your screen.
To really understand this invisible backend, you have to look at HTTP status codes. These are the standardized 3-digit responses the server sends back.
The language of the web.
Exactly.
Yeah.
When your API call works perfectly, you get a 200 OK. It's the invisible green light of the web. But when things break, developers live and die by the error codes.
Oh, absolutely.
A 301 moved permanently means your caching layer needs to update its records because the URL changed. A 400 bad request is a client error. Your code formatted the JSON payload incorrectly, and the server rejected it.
Then you get into the security and infrastructure codes.
Right. A 403 forbidden means your authentication token was recognized, but your role doesn't have permission to access that specific endpoint.
You're in the building, but you don't have the key to that room.
Precisely. The infamous 404 not found means you are pointing at a resource that simply doesn't exist.
But perhaps the most dreaded code for an infrastructure engineer is the 503 service unavailable.
Oh, yeah.
If you are staring at a wall of 503s, it usually means your upstream servers are completely overwhelmed, or a major cloud provider just had a massive outage in US East 1.
And don't forget the 429 too many requests. If you are hitting a third-party API too aggressively, their rate-limiting gateway is going to slap you with a 429 to protect their own load balancers.
Understanding these codes is the difference between blindly guessing why a script failed and surgically diagnosing a network bottleneck.
Now, navigating this incredibly dense global library requires serious information retrieval skills. If you are an engineer trying to debug a complex regex failure or an obscure BGP routing drop, Basic keyword searching just isn't enough.
No, you have to master advanced search syntax. Using quotes for an exact phrase is table stakes. You need to use exclusionary operators, like term 1 minus term 2, to filter out noise.
And if you type in title.term, you force the engine to only index pages where your exact error code is in the main header.
You combine those search dorks with vital technical resources. MDN, the Mozilla Developer Network, is the gold standard.
The absolute source of truth for web APIs in JavaScript engine documentation.
And of course, Stack Overflow, the massive community-driven forum where developers essentially crowdsource the debugging of highly specific edge case network errors.
But we absolutely must tackle the elephant in the room regarding search and problem solving today. Artificial intelligence?
Large language models.
Tools like ChatGPT or GitHub Copilot have fundamentally altered how developers interact with the web. They act as a hyper-contextualized search, synthesizing documentation into instantly readable code snippets for debugging or optimizing an algorithm.
However, as original researchers analyzing this ecosystem, we have to issue a severe cautionary note to you here.
AI models are fundamentally stochastic parrots. They are pattern matchers.
Precisely. They are not logical inference engines. They calculate the statistical probability of the next token based on their training data.
They can output a Python script for a custom routing protocol that looks incredibly authoritative,
Well commented, structurally perfect.
but relies on a network library that literally does not exist. It confidently hallucinates.
Which is incredibly dangerous if you are blindly copy and pasting into a production environment.
And beyond the immediate security risks, there is a massive risk to your own cognitive architecture. If you rely solely on an LLM to generate your network requests or build your APIs, you are outsourcing your understanding of the underlying systems.
You stop thinking about packet loss, TCP overhead, or how DNS resolution is impacting your application's latency.
We strongly urge you to map out the logic manually. Dig into the MDN documentation. Trace the packets.
Use AI to speed up boilerplate generation, sure, but build your foundational systems knowledge first. Otherwise, you won't even possess the baseline expertise required to realize when the AI is feeding you a dangerously flawed architectural pattern.
It's all about retaining sovereignty over the systems you are building. If you don't understand the physical handshake, you're just a passenger on the network.
This raises an important question. You usually ask this one.
I do. This raises an important question. We have spent this entire deep dive establishing that the internet is a deeply physical infrastructure, constrained by fiber optic bandwidth, BGP routing, and data center load balancing.
Right.
And we know that AI models require unimaginably massive scrapes of human-generated web data to function. So what happens to the global network's efficiency and the fundamental truthfulness of its information retrieval layers when AI starts predominantly scraping and pattern matching synthetic data generated by other AI models?
That's a chilling thought.
What happens to the physical infrastructure when it is choked by recursive, automated loops of synthetic traffic?
A question for another day.
This has been the RNA Deep Dive. We will keep the network running for you.
Keep exploring and expand your mind.